Swayam Prabha. Digital India. Educated India.
Welcome to lecture number 20. In this lecture, we will try to cover about ceramic matrix composites. Ceramic is one material which has been used for centuries together. In fact, the earthen pot is a very simple example for ceramic materials being used in the history. So, ceramic materials has its own advantage, and in the past itself, for example, in the previous century itself, people started using ceramics as a matrix and then reinforced with some soft materials, and then they have now recently we have moved to hard materials also. So, in this lecture we will primarily focus on introduction to ceramic matrix composites, what are different types of ceramic matrix composite, property of ceramic matrix composite, interfaces, then we will go through some of the fabrication techniques, and finally application of ceramic matrix composites. So, a recap till now, whatever we have done, we have studied of manufacturing of composites. In manufacturing of composites, we had three matrices. One is polymer matrix composite, metal matrix composite, and ceramic matrix composite. In polymer matrix composite, we have seen thermoplast, thermoset, and to some extent we also have seen elastomers. Metal matrix composite, we have seen aluminum based and then to some extent magnesium based composite materials, right. So, now we will focus on ceramic matrix composites. So, before getting into it, little bit of fundamentals. So, what is the typical difference between a metal and a ceramic material? Metal are crystal structures, ceramics are also of crystal structures. In metals, you have large number of free electrons. So, that is why it is predominantly conducting material. Here it is captive electrons are there. In metals, we have metallic bond, here it is ionic or covalent bond, that means to say it is very, very strong. So, since it is metallic and it has free electrons, it is good conductor. Here ceramics are poor conductors. Majority of the metals are crystalline or polycrystalline in structure. So, they are opaque, and here you have amorphous material also in ceramics. So, that is why it is transparent, and of course, you have crystalline, semi-crystalline and amorphous ceramics, all three, but if it amorphous is also one. So, amorphous we have transparent. A simple example is your glass, then it has uniform atoms. Here different size of atoms are there, that means to say semi-crystalline materials can also be possible. So, it has a very high ductile strength, here it has very poor ductile strength. Since it is all covalently bonded, the bond is very strong. So, it is tensile strength, very high tensile strength, here it is very poor tensile strength. So, here since they have free electrons, and these free electrons and metallic bond, they give you some amount of ductility, here there is no ductility. So, that is why it has very poor tensile strength. It has very low shear strength, it has very high shear strength. It is good in ductility, it is poor. It can plastically flow, here that property itself is not there. It is very good in impact strength, it has very poor in impact strength. So, that is why it is brittle. It is relatively, it has a heavy weight or high weight, or it has a higher density, here it is low weight or low density. Hardness is moderate, hardness is extremely high. So, predominantly if you look at ceramics, extreme high hardness, poor ductility, poor tensile strength. So, it is non-porous. Here you can also have porosity in ceramics. It has very high density, it has very low density. So, now with this you can try to identify very clearly what is the difference between metals and ceramics, when to go for metal matrix, when to go for ceramic matrix. Wherever you have very high temperature application, we always prefer to have ceramics. Wherever you would like to have very light and where there is not much of impact load, we always go for ceramic matrix and ceramic matrix composites are made. If you look at ceramics are divided into two. One is called as traditional ceramics, the other one is called as advanced ceramics. So, traditional ceramics, you have white wares, and then you have structural clay products, bricks and tiles, abrasives, which is used in grinding, which is used in water jet cutting, which is used for lapping, polishing, all those things. You have refractories and you have cement. These are the traditional ceramic materials which we know, and lot of products have been used. Okay. And when you go for advanced ceramics, you have electronic ceramic and you have advanced structural ceramic. Predominantly, our focus will be on structural ceramics. So, in structural ceramics, you have nuclear ceramics, bioceramics, tribological ceramics and automotive ceramics. So, bioceramics, which is used as bio implants into the body. When you look at electroceramics, we will have electronic substrate. For packaged ceramics, we will have capacitor, dielectric or piezoelectric ceramics, magnetic ceramics, optical ceramics and conductive ceramics. So, all these things are electroceramics. This is a new area which is there from the last 50-60 years, and today we are finding lot of applications in these areas. For example, magnetic ceramics, which is not thought of, is now there, and we also have capacitor dielectric ceramics, which is for very small applications. We also have piezo crystal ceramics, where in which very small displacements are to be measured, are to be given, we go for piezo crystal ceramics. So, when you talk about matrices, so since ceramic is the form of existence of ceramic is always in powder form, so the reinforcement whatever we mix has to also be somewhere close to powder form. So, we always use particulate. So, we always use particulate, whisker, we use nano powder or nano whatever. So, these are the three reinforcements which are predominantly used. The form can be particulate, where in which we talk about aspect ratio, then whisker, then you can also have nano. So, these are some of the reinforcements which are added to the matrix ceramics to get a ceramic matrix composite. So, matrix can be of two types, it can be oxide and it can be non-oxide. When I talk about oxide, it is TiO2, Al2O3, SiO2, all these things can be there. When I talk about non-oxides, it can be SiC, SiN, TiC, TiN, TiCN. These are some of the non-oxide ceramics which are there. So, you can choose depending upon your requirements, choose any one of these ceramics as a matrix, and then this matrix is blended or mixed with these reinforcement, and finally you get the output ceramic matrix composite. So, we can see that. So, these are the matrices. You have SiC, Si3N4 silicon nitride, molybdenum silicide, boron carbide, boron nitride, aluminum nitride, TiB2, TiN, TiCN and alumina, which is very commonly used. So, if you see the particulates, we can see TiC can be there, SiC can be there, TiN can be there, TiB2 can be there. You can have zirconium oxide, you can have niobium, and you can have silicon nitride, B4C we have seen. So, it can be in platelet form, it can be in whisker form, and today we have also started using fiber form. So, fiber is, you will have a fiber which is made out of metal, and this metal will be coated with ceramic material. So, this is a coating which is done on top of ceramic. So, now the fiber is called as ceramic fiber. So, predominantly this is done by CVD process. This is done by chemical vapor deposition process. What we give is, say for example, you can have a tungsten wire and then which is coated with boron. You can have a carbon fiber also. So, you can also have alumina fiber wherein which it is coated a ductile wire, tungsten or something which is coated, because tungsten is very high temperature. So, when alumina is coated, it can withstand very high temperature applications. So, ceramics are subgroup of composites as well as a subgroup of technical ceramics. By definition, ceramic matrix composites are materials in which one or more distinct ceramic phases are intentionally added in order to enhance some properties that is not possessed in the monolithic ceramic. So, so the biggest thing what we are looking forward is we would like to enhance the toughness property. So, the toughness property can be enhanced by adding particulates. What happens when you add particulates? When you have a ceramics and when you add particulates in it, and when a crack grows, the crack is getting diverted or distributed, or the crack energy is reduced and it goes around the ceramics, and then it goes. When it goes around the ceramics, the energy is dissipated, and because of this dissipation the crack does not go further. So, the toughness property increases. So, this is the particulate or particle, whatever it is. So, what I have done? I have intentionally added these particulates such that I can enhance the toughness property. So, that is what we are talking here. In ceramic matrix composite, a given ceramic matrix is reinforced either with a discontinuous reinforcement or it can be with the continuous reinforcement. Predominantly what we look forward is discontinuous. So, it can be in particulate form, whisker form, or it can be chopped fiber. The continuous fiber is also possible. So, the basic reinforcement which are included in the ceramic matrix are carbon, glass ceramics, oxide and non-oxide ceramics are added to the basic ceramic matrix. So, if you look at the SEM figure of a ceramic matrix composite, you can very well see this is a matrix and you can see this is the alumina fiber which is reinforced. And this is what I was trying to say, if at all there is a crack here, this crack goes around and the energy is dissipated. So, you can see this is 5 microns. So, this reinforcement may be somewhere around about 10 to 15 microns. Okay, this is an alumina fiber, this is one cross section. So, you can see how it is done. So, reinforced by 2D woven fabric, they have done it with using a 2D woven fabric. So, the fracture toughness of the ceramic is improved by introducing a secondary phase which we were discussing. So, I was saying that the secondary phase are chosen to act as a barrier for crack propagation. So, is it clear? Whatever we have seen here in the previous SEM, we have just put it in words. Predominantly in ceramic matrix composite, we will try to enhance the toughness property, that is one property. But if you want to make it conducting ceramics, so we try to add ingredients such that it makes the ceramic conducting. So, there we choose conducting particulates to be added and then people start using it. Today people have started using CNT in a big way, so that they would get advantages over the toughness property. The whisker and particulate, the difference is aspect ratio, is introduced into the ceramic matrix for retaining the crack propagation, because the stresses in the whisker spanning the crack plane will tend to pull the crack shut. This phenomena is called as crack bridging. Crack bridging is one very important phenomena, very important phenomena. What is this phenomena? Here the crack propagation so what happens, the whisker when it is introduced into the ceramic matrix, it can retrade the ceramic propagation, because the stresses in the whisker spanning the crack plane will tend to pull the crack shut, and this is called as crack bridging, which leads to very high fracture toughness. When we are using continuous fiber composite, it exhibits quasi ductile fracture behavior resulting in extensive fiber bridging. But please understand, using or reinforcing a ceramic fiber into the matrix is really a challenge while manufacturing. It is very easy to manufacture particulate type or whisker type ceramic matrix composite. Simple example is your cutting tool, wherein which we use tungsten carbide and cobalt. Then you can try to say add tungsten carbide. Today we add cobalt, and we also add zirconium oxide. This is also a cutting tool which people have started using, right? And then you can also use alumina, which is reinforced with SiC, which is in the whisker form. All these things are done only to enhance the fracture toughness behavior. So, there are two categories of ceramic matrix composite. One is a group of toughened ceramic reinforced with a particulate. The second one is a continuous fiber composite which exhibits quasi-ductile fracture behavior accompanied by a extensive fiber pullout. So, basically what happens is, when the crack tries to grow around the particulate, either this particulate tries to distribute and do something, or the fiber or the particulate pulls out of the existing location, so that all the energy gets dissipated in pulling it out, so the crack does not go further. So, the fracture toughness of this class of material can be higher than 20 megapascal root meter when produced with a weakened interface between the fiber and the matrix. For example, what are we trying to say? Let us go back to the SCM we were discussing. So, one way of doing it is the crack which is growing here. One way is you distribute the crack energy. The other way is, the crack is growing, you try to pull this particulate out, or you try to pull this fiber out. When you try to pull the fiber out, the energy gets into pulling it out, because you have a very weak interface. Weak interface means it quickly goes around and tries to remove the particle very easily, and the energy is dissipated into the fiber in that location where the pullout has happened. So, different types of ceramics, alumina, zirconium oxide ceramics are there. SiC particulate reinforced in silicon nitride, again a cutting tool usage. Then alumina and SiC. Then we have this is whisker. First one was particulate, this was whisker. Then you have continuous fiber. Then carbon-carbon composite is there. SiC. These are all very high temperature application, high temperature, which is used in missile, rocket, all those things. Oxide composites are also there available. So, for example, alumina reinforced with an alumina particulate, or alumina reinforced with zirconium oxide. So, alumina reinforced with SiO2. So, these are some of the examples. So, what are the different types of composites, ceramic matrix composite? It can be short fiber, it can be long fiber, it can be layered, it can be particulate, it can be functionally graded ceramics. Look at the functionally graded ceramics. The reinforcement, if you see layer by layer by layer, there is the volume fraction keeps changing layer by layer by layer. So, what happens? On the periphery you have a large amount of particulates, as and when it goes down it is less. Because of this, what happens? The tribological property and fracture toughness property enhances. This is functionally graded material. Today there is a huge demand for functionally graded materials. Then you can have polycrystalline with different fracture properties of grain boundaries you can have. Then particulate with small interface, these are interface, and then particulate with very thick interface. So, these are the different types of classifications of ceramic matrix composite. I repeat, it can be short fiber, or if you want you can go one step ahead. Okay, short fiber, then you can have long fiber, then you can have layered. Layered are basically something like a tape type, you try to cut it down, or you try to make a preform or something like that. So, you get that, and then today you have ceramic tapes which are available. So, you put those tapes as and when you want to reinforce. Then you have particulates, right? The difference between this and this is aspect ratio. So, here particulates can be viscous, it can be particulates. The distribution of particulates between layer to layer to layer, there is a variation which leads to functionally graded materials. So, functionally graded materials, if you see the function, you try to reinforce, the function grades along the material. So, if you see after you remove the first 3 layers, then the tribological property will be less. Then you have polycrystalline with different fracture properties of grain boundaries. These are grain boundaries. Then you will have with weak interface with strong interface. So that means to say this interface, the crack can grow, break, it will yield out, and then you get the required output. So what are the properties of a ceramic matrix composite? Generally, when you make a product, first thing what you have to look at is you have to write down the objectives, or you have to write down the specification. What is the specification this product has to execute when put on service condition? So that means to say we will always try to list down all the properties what you want from this material, plus you will also try to put a quantifying value for each of the specification whatever you say. Okay. So with this what you get is you get the properties. Moment you have these properties, then you start working on which matrix to choose, which interface to choose, what is the processing route, and how do I meet out to the requirements. So if you want to make a ceramic matrix composite, so first thing is you have to understand what are the properties of ceramic matrix composite. So ceramic matrix composite, the property which is common for all composites is it has very high strength to weight ratio. Ceramics of its own has very good wear resistance. So ceramic matrix composite will have wear resistance properties. Ceramic matrix will have corrosion resistance. Now since it is ceramic matrix composite, its fatigue strength is enhanced. Suppose for ceramics you want to enhance the fatigue strength. So then basically what we do is we convert it into ceramic composites. Then we have low electrical conductivity. You can add particulates to change this property. It has anisotropic property. It is low cost. It is easy for processing. The matrix is harder and brittle. The reinforcement must have high tensile strength to arrest the crack growth. This is very, very important. The reinforcement must have high tensile strength. Then the reinforcement must be free to pull out as the crack extends. So basically what you do is the energy which is getting dissipated into the product. See, the energy when it propagates, it should spend enough of energy so that it pulls out the fiber or it pulls out the particulate. So once it pulls out, the energy is dissipates. At that point crack does not grow, the material retains for a longer time. So the fatigue life enhances, the toughness value goes high. This is typically, I have just put different ceramic matrix composite, and I have put the ceramic matrix, what is their properties. When you talk about porosity, density, you see alumina 3.8, when you make alumina it goes to 2.1. You have tensile properties, you have elongation, you have Young's modulus, and then you have flexural strength. Young's modulus means, higher Young's modulus means it is becoming harder, it is brittle. Like there is no elongation at all. Okay. So you can do with carbon reinforced with SiC, then C with SiC. These are different process which we will see later. So the other properties which people are now trying to enhance on a ceramic matrix is they wanted to enhance the thermal conductivity, they wanted to enhance the linear expansion and the electrical resistance. So these are the values of different processes. So the property of ceramic matrix composite, if you see in the it is exhaustively used in aerospace industry and turbine engine. If you see in aerospace engine, the temperature what we talk about is above 1500 degrees Celsius, here it is above 1000 degrees Celsius, and in turbo engine components or heat exchangers it is expected to work for 10,000 hours. Okay. And when you have a sliding and a sleeve or in a pump components, it is expected the temperature will go up to 500 degrees Celsius, the temperatures, the working hours is going to be from 1000 to 10,000 hours. So here what we are looking at it, we are looking at properties which can enhance the temperature, which can withstand for a longer temperature, which is light in weight, the fracture toughness is high, and tribological properties. Okay. So long lifetime under extreme temperatures, that is oxidation and wear. So we also are talking about oxidation resistance and corrosion. oxidation and corrosion resistance are some of the properties which we always expect from ceramic matrix composites. I already discussed this interface and interface. I will reiterate the same thing. Interface is very important because if you want to enhance the crack propagation, so basically what you have to do is you have to enhance the interface property. So it is the boundary demarcating the distinct face of the reinforcement and the matrix. This is a zone across which the matrix and the reinforcement face interact. The interaction can be chemical, it can be physical, it can be through mechanical. Mechanical means it can be through locking, mechanical locking, right. For the composite to operate effectively, the face must bond where they join at the interface. In some cases, the third ingredient must be added to achieve bonding of primary and secondary face called an interface. Is it clear? This third ingredient can be through an additive or a coating. So basically it is some reaction happens between these two, between the matrix and the ceramic which is reinforced. So now what happens is there is a reaction happening and it can form an interface. So this interface is between matrix and the ceramic, and this interface is between these two. We try to functionalize so that you get a proper this thing. So this we have already discussed. I just wanted to put it for a reiteration. So interface, what is interface? Right? Is it clear now? We studied in metal matrix composite also. I have just wanted to reiterate the same thing. So interfaces, little bit when you look at mechanical strength and other things. So here we see a brittle fracture, here we see a non-brittle fracture. So these are the mechanisms of the crack deflection which happens in a ceramic matrix composite. You can see here, if it is a brittle fracture, so the crack just keeps propagating in this direction. Fiber break, these are the fibers, these are ceramic, it breaks. So no interface of the fiber on the fiber surfaces are there, so it just breaks like this, right. The next one is, if it is a non-brittle fracture, there is a debonding at the interface of the fiber and surface. So what happens is the crack gets distributed. So this interface tries to distribute the crack, so it is going to withstand higher amount of toughness. So here additional interface layer, for example a film of SiC of thickness 0.5 to 5 micron provides protection of the fiber from either the environmental attack or the aggressive action of the infiltration of the material. So this is very important. So this happens, this is the importance of interface between a fiber and the ceramic matrix. The mechanism of failure can be brittle or it can be non-brittle. So the debonding at the interface happens here, it just crack propagates and then it breaks all the fiber and because it has no interface. So the interface can influence the composite strength, modes of failure, Young's modulus, interlaminar shear stress, compressive strength, environmental resistance, sustainable at higher temperatures, and fracture and fatigue behavior. These are all important properties for interface. Very, very important. Important for interface in ceramic matrix composites. So the cracks at interface you can see here. This is alumina, this is zirconium oxide. So this is the diameter of the they are saying 2.5 microns. This is the small reinforcement which is there. So we can have, these are the cracks at the interface, these are the cracks, and then you can see a unit cell A with a meso cell level you can have, and we can make this. So you look at it. So these are nothing but wing cracks at micro level between the interface. So these are meso cracks, these are wing cracks, micro level cracks which happens and the crack keeps growing. So you see beautifully the crack keeps going from here to the next crack. And the other thing is a micro level crack between the grains it can have. And the last one is the second kink initiative of the wing crack. So you can see here. So here it again it bifurcates and it starts growing, and these are the loads when they are applied tensile load which is applied. So, you can see what happens to the crack and how does it grow. So, in all the three cases you see the important thing is tensile is loaded, it is loaded tensile, and because of that the crack keeps growing. So, this is wing level, micro level crack, this is meso crack, and then this is secondary kink initiative for wing cracks. So, the most important property between the ceramic which is used as a particulate and the ceramic which is used as a matrix, between these two fellows to have a very good attachment or something, we need to look at their wettability property. Wettability property becomes very, very important. So, wettability property, the liquid which spreads over the solid is wettability. Good liquid wettability means the liquid matrix will flow over the reinforcement. Here it is already ceramic, so you can't take it to the liquid phase. So, you have to say how do you make this wettability property very good. The wetting will also occur if the viscosity of the matrix is too high, the interfacial bond exists due to adhesion between the reinforcement and the matrix, which means to say the wetting is good between the reinforcement and the ceramic matrix. So, we have already seen it in the metal matrix. So, the same figure we are repeating here for ceramic matrix also. You have a vapor state, you have a liquid state, you have a solid state. This is a line which talks about the interface between the solid liquid, between an interface which talks about liquid vapor, and this is an angle which is made. So, and this angle is called as the contact angle. We are more interested to find out the contact angle, and here I have forgotten to say this is an interface between the vapor phase and the solid phase. Okay. So, if this theta is 180 degrees, then it has no wetting angle. If it is 0, it is perfect wetting angle. So, this goes to 0. So, it goes down. So, it is perfectly wetting, and if it is anything between 0 and 180, 0 and 180, the wetting the degree of the wetting angle increases or as theta decreases. So, when you go lower and lower and lower, wetting is good. When you go higher and higher and higher and higher, it is not good, or it is having a poor wettability property. So, this can be found out by the formula cos theta equal to gamma Sg minus gamma Sl by gamma Lg. Okay. So, Sg is solid and gas, solid and liquid, liquid and gas. So, if you want to look at it, solid and liquid. Okay. So, this is solid and gas, solid and vapor, and so we can make it as G, and this we can make it as this we are making it as SL, this is Crite, and this is Sg, vapor is Sg, right. So, this is what is the formula, we try to find out the cos theta. This is wetting and poor wettability, lotus leaf effect. So, majority of the insects, leaves and all, they have a nanofiber, or they call it as nano texturing, nano/micro texture on the surface of the leaf. We have this nano or micro texture. So, this makes it have poor wettability property, so that the water droplet rolls out of the thing of the leaf and falls down. The same is with respect to lot of animals on their skin. For example, shark, which is always in water, never has a skin disease. Why? Because of the micro nano texturing. So, here it is all more focused towards wettability. Globally, ceramic matrix composite in the last couple of years, what has happened is slowly it has been started getting increased in different areas where mechanical and chemical applications. So, it is there, it is used, for example, it is used in heat exchangers, it is used in extraction units, oil refineries. Now, when they are looking forward for chemical, aerospace and defense, if they wanted to make it lightweight material, they are looking for energy and environment, they are also looking for ceramic matrix composite, and others are there. You can see slowly the manifold from 2005 from $250 million, it has gone to close to $450 million. So, this from $100 million, it has gone down to $220 million. So, the other industries are also there is lot amount of usage of ceramic matrix composites. So, what is the next generation of ceramic matrix composite? So, the next generation of ceramic matrix composite are going to be so these are TBCs, this is thermal barrier coating. Thermal barrier coating can be used for aerospace, cutting tool, so many applications. First it was uncooled, now it is film cooled, then with thermal barrier coating, then with EBG we are also now getting materials which are silicon based ceramic matrix composites are there. We are now then this will go into eutectic oxide based ceramic matrix composite with heat pipe cooling we will try to make. So, you can see these are the ceramic materials which can go up to 3000 to 3500 degrees, can go up to 3500 degrees Fahrenheit. So, this is what we are looking at it. We are looking at high temperatures and very high temperature we are looking at, and now we are also looking at very good mechanical properties such that it can be used for that. So, this is electronic barrier coating, thermal barrier coating. So, electronic barrier coating silicon based. So, here we are looking at these are the first generation, these are the second generation, and now it goes. We will move towards the application of ceramic matrix composite. It is today exhaustively used in automobile brake lining. What happens nowadays, we talk about very high speeds. So, the very high speeds, if you apply brake, there will be a lot of heat which is getting generated. So, there will be thermal expansion and softening of the material which we do not want to happen. So, we are nowadays going for CSIC rotors and we also have cooling channels. These are the bells which are used, and these are tungsten pads which are used. So, when these two come in contact, so we would try to get very high temperatures and there will be very high frictions. That is reduced when we start using ceramic matrix composite. So, carbon with SiC. So, high braking performance, the weight goes down, the wear resistance goes down, the temperature of which it is operating goes very high up to 1400 degrees Celsius, and nothing happens. The first study started in 1990 and it is available from 2000. It has been introduced in Mercedes and Porsche cars. It has been introduced. There are 50,000 to 70,000 ceramic matrix composite brake discs which are manufactured in 2006 by these two companies. So, if you look at it, these are ceramic matrix composite rotor on a BST carbon fiber wheel. So, carbon fiber wheel is very lightweight. So, paired with Bembo monoblock capillary, custom anodized spacer and bottom of this super high bike forks. So, you can see this. So, these are the forks, and this is completely now made up of ceramic matrix composite. This is what the monoblock caliper, which is monoblock caliper which is used. So, this is best for our braking. This is the carbon ceramic composite disc brakes which are used. So, these are the disc brakes which are used in automobile today. So, the Porsche ceramic composite clutches are made out of it, which is called as PCCC, Polish ceramic composite clutches. Okay. Designed and the siliconized carbon fiber fabric is used here. The diameter is around about 170 millimeter, the weight is around about 3.5 kgs. Earlier it was made out of cast iron which was like 7-10 kgs, now it has come to 3.5. 1/10 of the mass moment of inertia comes because of this ceramic matrix composites, which is a huge reduction in energy consumption and all those things. Lower transmission and engine mounting, lower center of gravity, and it is very high. Since the technology is not become popular, it is an intellectual property technology, so still it is expensive. So, you can see that in transmission systems also the ceramic clutches, here are ceramic clutches which are there, and these is engine and you have transmission. So, now in transmission and in ceramic clutches they are using ceramic matrix composites. So, in the nozzles, in the aerospace nozzles which we use, F-16 fighter planes, right. So, the engine exhaust nozzles with 5A500 ceramic matrix composite divergent seals which are, these are the divergent seals which are made out of ceramic matrix composites. So, they are, and ceramic matrix composite are an excellent replacement for nickel based superalloys. Already these nickel based superalloys are very light in weight. Manufacturing is a big challenge of this, but whereas ceramic matrix composite, the manufacturing to large extent is as compared to this, it is very easy. So, currently uses exhaust nozzle parts, and primarily due to their high capacity of withstanding very high temperature and severe environmental conditions. So, very high temperature, severe is, it can be tribological, it can be low and high temperature. So, for example, all these fighter planes go at minus 35 degrees C, it can go up to maybe somewhere around about 900 degrees C, or it can be also up to 1500 degrees C. So, this is the ambient temperature when it goes at very high altitudes. This is the working temperature when it is burning. So, there has to be minimum structural changes, there has to be minimum distortion which is happening, and it has to retain its shape. So, an oxide ceramic matrix composite exhaust ground demonstrate, which is around about 1.6 meter diameter nozzle. This is 1.6 meter diameter nozzle, and it is one which is also which is in a conical shape. Fabrication is a big challenge. Now, it is made out of ceramic matrix composite with a titanium cap on top of it. So, a complete turbine is made out of ceramic matrix composite, or the parts which are there are made out of ceramic matrix composite. So, invasion. So, what they are trying to do is, first they are trying to attack at lower pressure compressor side, and then they are looking at higher pressure composite side. So, here they will make ceramic matrix composite either as insert or as a whole body, whole part body, right. So, do not think completely the turbine will be made. So, either they can make small inserts. For example, they can make a small insert here of very high temperature withstanding, and then they can also make the whole body is, what I am trying to say is, a small portion wherein which it gets attached to another big portion of the entire system. So, combustor is there. So, here you will have high pressure turbine and you will have a low pressure turbine. So, high pressure, so here it is a compressor. So, high pressure compressor and high pressure turbine, low pressure turbine. Today they are made of ceramic matrix composite material, because they have these CMC has toughness very high, and making small inserts is very easy as compared to making a complete body. So, there is lot of aero engine which is made out of composites. Now, CMC is getting envisaged in all these things, so that it can be made lighter and lighter. So, SiC nuclear application is other thing. Today we talk about SiC, silicon carbide reinforced composites, which are used for advanced structural materials in fusion and fission energy systems, wherein which the heat resistance and integrated safety is also there. So, this is now thought of. SiC in nuclear application is the next place where ceramic matrix composites are talked up in a very big way. So, when you talk about fusion, the temperatures are very high. So, the blanket structure, the blanket channel liners are made out of ceramic matrix composites. So, jet engines, turbine blades, which we have already discussed. See, if you look at it, these are some inserts. This is a part. Here is a joining adapter, and this is a slot. So, they are now made out of ceramics. Then you can also see hot fluid channels are there. So, these are all made out of ceramics, or these are all so that it can withstand very high temperature and corrosion resistance. What is the advantage of ceramic matrix composite? Excellent wear, excellent corrosion resistance, strength to weight ratio, elevated temperature retaining the structural properties, chemically stable, catastrophic failures because of the reinforcement, the cracks can go, high hardness and light in weight are some of the major advantages of ceramic matrix composites. So, the advantage, the processing route of ceramic matrix composite involves very high temperature and can be deployed only with high temperature reinforcements. So, wherever you need a very high temperature application, there we will use this. The ceramic matrix composites improves toughness. The processing of temperature results in the complexity and manufacturing, and hence the process becomes costly, then the difference in coefficient of thermal expansion between the matrix and the reinforcement of thermal stresses on cooling for processing temperature is very, very high. So, the disadvantages of what is the processing difficulty and other things. So, the biggest disadvantage is since it has to be processed at very high temperatures, we have to have furnaces which can withstand very high temperature, and the reinforcement also should be of very high temperature withstanding. So, that is one of the disadvantages of ceramic matrix composite. 2, it is used to enhance the toughness property. So, because of the toughness property, you also have to see the match in the grain size, the match in their properties between these two. So, the next thing is, since it is higher processing temperatures are there, all these there is lot of complexity and the process is pretty expensive. The difference in the coefficient of thermal expansion between the matrix and the reinforcement leads to thermal stresses on cooling while the process is made. This has to be taken care while choosing the ceramic and the reinforcement for making ceramic matrix composite. So, this is expensive, this is challenging, and this is also, these three properties are these three are the biggest disadvantages of ceramic matrix composites. Okay, for this lecture assignment, so what I would request you is, I would request you to pick some ceramic parts or products, right, and try to replace or add some particulate to the ceramic product. And see its performance. For example, take clay. Clay is a ceramic material, ordinary clay. Try to add abrasives to it. Try to add abrasive. Abrasive means sand, ordinary sand, which is nothing but SiO2. Try to add to it. Now, you try to make something like a cup or pot or a part, whatever you want, a very simple trivial part. So, what you do is, first take clay, and then what you do is you try to fire the clay. The firing of the clay can be done on a microwave oven, or if you have a furnace, you can put it in a furnace. Maintain it at slightly higher temperature. So, around about 800. We are not looking for a very sound quality, but just for your understanding and experimentation sake. So, 800 degrees Celsius, if you have a furnace, you can put, or you can just put it in a microwave oven and keep it for some time, maybe 2 minutes or 3 minutes, and see before it forms any cracks, you have to pull it out of the microwave. So, you can put it in a microwave and then try to make one again. So, cup / pot, whatever it is. Next, you take clay, mix with some volume fraction of SiO2, and then first see what happens in the formability while making a shape, what happens, and then when you try to put it inside microwave, what happens. Just qualitatively make a comparison. And then just for yourself and study. Comparison and study for yourself. So, you will make a clay. So, the steps involved, if you want, I can you take clay, give a shape to it, and then put it inside a microwave oven and make sure it does not crack and allow it to dry. The next thing is a clay mixed with abrasive. Again, you will try to shape, put it in a microwave and then allow it to dry, right, and then you will try to compare. So, here SiC is a reinforcement agent. Compare what? Compare strength, compare formability, compare the crack if it is growing, and finally you can also compare it with respect to sound. So, just hit it with another surface and then try to note down the sound, how shrieking it is coming and other things. So, this is an assignment which will try to give you an understanding of ceramic matrix and ceramic matrix reinforced ceramics, so that you compare the processing difficulty and the other properties with respect to these two. Thank you.